You never know when these things have started, but it looks as though it started the end of the intro, and we're here. And once again, I have to welcome you aboard MEL Science. My name's Dan, and it's lovely to have you here. Although I can't see you, I can't hear you, and sadly, hopefully, I can actually see you typing. So as soon as M Law has come into the building, excellent, and hi to you too. So just to start with, once again, welcome to MEL Science. My name is hello Mindy, hello, lovely to have you on board, and Vazzy, hello Vazzy. So again, please do let me know when you come in, say a little hello, so I know who you are, and I can make it a little bit more personal than Julie, and Zin, and Toby, and Zim. Fantastic. Great to have you guys and girls all on board today. So wait a couple of minutes for everybody to sort of get settled in, and then we'll crack on with the science, as always. Enda, hello Enda, and Amelia, hello Amelia. And again, apologise, I sort of keep leaning in because I've got to sort of see your chat on the screen in front of me. It's not on a big screen, unfortunately, so I can't just read it. Good morning, Kenzie, good morning. Kenzie, it might be good morning for you. It's good afternoon from me. Eniko, hello Eniko. I have a whole lot of new names here. I don't recognise any of the names so far. Yizzy, Devon, from Yizzy, so you all know that it's 5 o'clock in the afternoon. Hello Ella, my name is Ella, I'm from Scotland, but I live in France. Okay, fantastic. Are you in France now? Who knows? You might be in the night, in the warmth. Just get rid of this little poll for a second. And from Tilly and from Surrey, excellent, hello. And it's going to be rainy and miserable like it is here in Birmingham, I think. Nicola, Spike and Poppy. Hello, Nicola, Spike and Poppy. What a lovely name, Spike and Poppy. Fantastic. Great. So we have quite a lot of you today, which is absolutely lovely. So today, ladies and gentlemen, we are doing water, pure water. This is an amazing set. Amazing bit of chemistry. It's very busy. There's a lot of stuff to do today. So I'm going to slow down today. South of England. Amelia. Hello, Amelia Boxall. And Nicola. Hello, Nicola. So I'm going to slow down when we go through the kit. There's a lot of kit to get through today. 3 wonderful experiments. And I must warn you, ladies and gentlemen, I must warn you that one of the experiments, the last one we do today, is quite scary. It's quite a bang to it. Okay, so you've got to have nerves of steel. As you know full well, in being a scientist, you have to have nerves of steel. So have your nerves of steel ready, because the last one gets a nice bang when you're doing it properly. And actually, the historical precedent for this experiment is absolutely awesome in chemistry. We need pure water. We do indeed. So before I introduce some of the chemistry and some of the science, let's have a kit check. Just make sure you've got all your kits. I'll just switch cameras so that we can do this little kit check. So once again, today we are doing pure water. So this is the kit that you should have. Right, in no particular order. Hi, we have 3 kiddos watching from Florida. Brian, no problem at all. You can watch, because of course, as I said many times before, these videos, if you've not got the kit, you just want to watch, these videos are available on the web next time. So when you've got the kit, and you can pause those pre-recorded ones. Is there a bang in it? Ella, there is a bang. It's a very frightening bang, this one's here. Nerves of steel, as I said. So if you want to watch this and then do it later, that's perfectly fine. So you have your 3 experiment cards, so I'm going to go through the 3 experiment cards. So we're going to go carbon filter, we're going to go ion exchange resin, and then we're going to go bang with the oxyhydrogen at the end. You'll need some scissors, access to some scissors, you need your safety specs, you need your gloves, you need a glass beaker from your main kit, so the starter kit that comes with your MEL subscription. You need your glass beaker, you need your conical flask, you need the filter funnel, you need your plastic 250ml beaker. 1,000%, excellent, Ellen. That's the commitment we need from you, Ella. You need some little tiny beakers, some plastic beakers from your kit. Right, you also need 4 AAA batteries. So 4 AAA batteries. You need access to some hot water. I've got a flask here, so I'm going to use some boiling water in here. It's not quite boiling, obviously, but you need some access to some hot water. You also need access to some matches or a lighter. It doesn't have to be a match. If you want a lighter, that's perfectly fine. And from your kit, so there's quite a lot of kit here, so I'm going to spend a little bit of time going through some of the science while you just check all your kit as well, just to make sure we're all in it together. Okay, so starting with sodium carbonate. So you need some sodium carbonate. Now that's a liquid. You also need some calcium hydroxide, so there's some powdered calcium hydroxide. You also need, that's calcium hydroxide again. You need the methylene blue, so methylene blue dye, so methylene blue. You also need copper sulfate solution, so that's the light blue solution, so don't confuse these two. So when you're checking the labels, make sure this is methylene blue, and then you've got copper sulfate, which is also a blue liquid, so just make sure you check. The methylene blue is a much deeper coloured blue solution. You also need the little tube that says resin on it, and that's full of little powdered balls, little sort of plastic-looking balls with resin. And then you need some ammonium carbonate, so ammonium carbonate here, and you also need carbon, some so fine powdered carbon. Okay, so those are the chemicals we need from the pack. Also from the pack, it's very busy, this one, very busy. You need the little tiny pot holder. So this is a tiny pot holder or container holder. You need your filter papers. So filter papers, you only need one of these, but because of course within the kit there's enough to do 3 different experiments. All experiments twice, sorry, I mean. You need your little battery pack. You need one of the little tiny electrodes, so one of the little tiny electrodes. Now yours might have a sort of silver one, or it might be a goldy coloured one, but you only need one for the time being. You need your spoon, so your plastic spoon. You need this is a really tough little container. So this is where we're going to make our little explosion at the end. It's not a little explosion, a nice big explosion, but you need this really hard, toughened plastic container. From your kit again, you need the one-hole bung, so the one-hole bung. You also need your syringes, so some syringes from your kit. You need the candles. I love explosions too. It's one of the reasons I teach chemistry. Fantastic. If you're not making something bang or burn, you're basically not doing chemistry. You also need leads, your connecting leads. Now please take care, ladies and gentlemen, that we have some pipettes here with the tops chopped off. So you need a couple of those with the pipettes with the top chopped off, and then there's one pipette that's whole. Can you see this one here? Look, hasn't got its top. So this is the bulb pipette. We also need that plus the ones without, the ones that have had their ends chopped off. Of course, as always, we need our little tiny paper clip to depress the plugs, the safety plugs inside the containers themselves. Okay, I think that has. Oh, sorry. Last but not least. You've got 4 little containers, 4 little plastic containers. Now you can wash these out. So after the experiment, just wash them out if you want to repeat them, when you want to repeat the experiments rather. So just wash these out. But you need 4 of those little plastic vials. And then you've got some little wooden stirrers or spills. You need those and some of the bungs, some little tiny filters. And carefully in this pack, you've also got a little rubber seal. It's a little rubber seal as well, which we need for the experiment at the end. You need one of those. And I think that has it covered. Okay, cool. I'll leave the picture there and just quickly check, just to make sure, because I don't... Jake! Lovely to have you on board, Jake. It's always lovely to have you on board. I hope you had a good day, despite the rain. I'm pretty sure it's raining in Stockport, same as it is down here in Birmingham. Teed up, not a problem. So I'm going to leave that set up a little bit while I'll just do the introduction to a bit of the science quickly, and then we'll start with experiment 1. So we're going to start with the carbon filter one today. Okay, so can I just check? Is everybody okay? Does anybody like me to repeat anything just now? Ella's okay, cool. Emlot, you're okay? You're okay? Izzy's fine, lovely. Amelia's fine, superb. Awesome. So I'm sure then everybody's good. Cool. Pauline, thank you. Zulin, Enda, and Scott. Lovely, lovely. Thank you. Okay, good. You're all good. Right, if you don't mind, just very quickly, as I said, always introduce a bit of some of the science. Why is this important? Pure water is so important. So if you see some here, the facts, not 780 million people don't have access to regular water in the world. Can you believe it? I don't believe it at all when I'm in Birmingham, because it's raining every day. But that's not the case everywhere in the world. It's just an enormous 780 million people don't have it on a regular basis. And if you look at one of the diseases, horrible diseases, diarrhea, of course, it's caused, or it kills somebody, die every couple of minutes because of a lack of clean water. This is a very serious topic. And then if you look at schools, about 433 million days are lost every year because of a lack of access to school, because of diseases and situations caused by lack of running water. So this is really important. This amazing molecule is absolutely essential for life on Earth in many ways. So today we're going to be looking at pure water versus impure water. And of course the impurities in water are different. And I'm going to explain what those impurities might be and how we might get rid of them. So just very quickly, everybody knows that the water molecule, of course, looks like this. It's H2O. That's what water is. If you look at it you know, in terms of shape and space, in terms of its atoms, it's got two little sort of Mickey Mouses and a big orange, sort of red Mickey Mouse nose. If you look at it a bit more carefully, it's O, ow. I'm just going to introduce this term to you. Okay, if you look at the O bit of it, it's negative. It's a negative charge. Now, like electrons are negative, like negative fields of a magnet sort of thing. And then the hydrogen bit is positive. So when you look at the water molecule, one part of it's negative and one part of it's positive, and that's become important a little bit later. And we'll go on to the history of that after the first experiment. Okay, cool. I'm ready for the first experiment. Ready for the first experiment. I'll set the first experiment up in terms of the equipment that we need, and let's crack on. Now, this is quite a short one, but it's very important, and it shows one way of getting some of the impurities out of water. Nice one, Jake. Fantastic. Good. Glad you're okay. Tea, crumbs from tea time being brushed aside, and the chemistry begins. Okay. Right, so what do we need for the first one? So I'll just move this aside. We're going to do this one first. Okay, so we're going to do the carbon filter first. I'm just going to put all the other bits and pieces aside that we don't need for this one. So we need, the little stand is one thing. I shall just put some of these chemicals over here. So it is a very busy setup, so just give me a couple of seconds to deconstruct the setup. Right. So we need also, whoops, a little cup. You need the stand. Whoops, let's not knock that over too carefully. You need one of the little tiny vials, the empty vials, and a syringe. And of course we're going to conduct it on our little tray. So I've got a cup, tray, and we don't need that. Okay. Now the chemicals we actually need for this one, of course, are carbon filter. That gives it away, the name gives it away. So we're going to use the carbon filter. Okay, so we need the activated carbon. So this is the activated carbon that we need for this one. Now we also need two little bungs, two little of our felt bungs. I can't hear you for some reason. Pranjal, can anybody not hear me? Is anybody else struggling to hear me? No, Ella, you're okay? No. I can hear you fine. Zim says I can hear you fine. We can hear you, Toby and Tilly. Yep, we can hear you. Kate, I'm sorry, Charles, I think it's probably your system somehow. Hearing well, lovely, loud and clear, awesome stuff, great. Okay, cool. So without much further ado, first of all we need our glasses, and we also need our gloves. So if you can put your gloves on now and put the glasses if you haven't done already, or is that just me? Okay, so whack the glasses on, and then get your gloves on. So whack glasses and gloves on. So get those on. So this is a really super. I don't have active carbon, I have charcoal, I hear you. Vasya, thank you. Yes, the carbon that's in your pack, we don't have carbon. Do you not have the carbon in your pack? Is Irie still cutting out? I don't think so. My system seems to think it's okay, so it might be internet somewhere. So you need this carbon. Now this is activated, never forgot the safety specs. Never forget the safety specs, Ella. Indeed, never forget the safety specs. So get your little gloves on. And just while we're getting our gloves on, does anybody know why the oceans are blue? It says charcoal on a bottle. It is charcoal, it's perfectly fine. It's the same thing, Amelia. Yep, that's perfectly fine. Anybody know why the oceans are blue? Anybody know why the oceans are blue? Pranjal! Classic mistake, Pranjal! Gotcha! No, they do not. The reason that the oceans are blue, sorry Pranjal, but good effort Pranjal, top cracking effort there, not in Blackfoot, Jake. No, of course around the UK the oceans are green, well the sea is green and grimy, but the oceans are blue because water itself, water the chemical, is blue. The water molecule is blue. And if you don't believe me, get a nice clean, I'm not doubting your cleanliness for a time, but get a nice clean bath, a white bath, and fill it up with water right up to the top, and you will see that it is a slightly blue colour. Water, the molecule is blue. Right, let's get cracking. So first things first, if you take your filter, so take this pipette with the top chopped off it, okay? Take your pipette with the top chopped off it and put one of the little tiny filters. Aha, Jake, you see, here to live and learn. So pop one of those into the top of your pipette like that, your split pipette, and with your little poker, your little stick, you then gently encourage that, poke it down into the bottom of the pipette like so. So poke that down into the bottom of the pipette. So that's the first thing you guys need to do, guys and girls. Okay, Vasir, that would be a nice explanation, but there's no diffraction involved in the watercolour. Okay, nice suggestion. I like that suggestion a lot. Everybody okay with that one? So, the next thing you do is get your charcoal or your activated carbon, charcoal activated carbon, or the black powdered stuff, and fill it up to the 3 centimetre cube mark. It's like a chopstick. It's not quite a chopstick. It hasn't got any tapering on it, and it's a bit thinner than a chopstick. But you could, nimble fingers, use it as a chopstick. Pranjal, but why does the water seem clear most of the time? Because in small volumes, water would appear to be colourless, but in very large volumes, its actual colour becomes apparent. Love that question. Thank you very much. Okay, so again, over your little tray, what you then need to do is fill up the pipette up to the 3 metre line, the 3 centimetre cube line, very gently like that, with the activated carbon. So just like that. So pop that into there like so. I'm just going to stick my lid back onto the carbon. And I will explain the science behind this. I will explain everything that we're doing here. And of course, all of these different experiments are designed to look at water, the properties of water, and actually how we can get pure water from the contaminated stuff. So then, if you also then get, finally, another little of the spongy filters, okay, and pop that into the top of your pipette like so, and then work that one in too. So just push that in and push it down on top of the carbon. So you should have a little tiny structure that looks like this. So this is our little filtering wing. This is our carbon filtering mechanism, okay? I love carbon. Yeah. You can't not like carbon. It's one of the most amazing elements there is. And of course, without carbon, we would not be here, okay? And if I had a magic wand and I went, kazz, and it removed all the carbon from you, just disintegrate into a little pile of sludge and foamy mess. Okay, so you should have a little filter like that. Right, so what we need to do is then take one of your little tiny vials. So take one of your little vials and pop it into the foam support stand like that, and then you can then pop your filter into the stand like that. Okay. Right, so now what we're going to do is we're going to create some muddy water, some impure water. And what we're going to do is we're going to put into a metal salt, effectively, which is, not sorry, metal salt, all that. What we're going to put in here is an organic substance. Methylene blue is an organic compound, okay? So if you find your methylene blue, so this is the methylene blue, okay? So remember, it's the dark coloured one. So take your methylene blue, and this is where we actually want some water in here. So we need to create a little bit of water. So I'm going to use some hot water. It doesn't have to be hot water. I've just got some water here. In fact, what I will do is my little jug of water actually over there. So give me 3 seconds. Give me 3 seconds, just so I can nip out and get some water. So give me 3 seconds. Hang on. Ta-da! Okay, for the discerning scientists, that might have been 5 seconds. Okay. Okay. So in your little plastic cup, if you pull it up to about the halfway line, so just about halfway, with some water like so. And now we're going to create some impure water. Disappearing down, indeed. It doesn't disappear very often, Jake, but he's reappeared now. So take your methylene blue. Now, if you haven't already, where did I put my little pin? I seem to have misplaced my pin. There we are. There we are. So take your little paper clip as usual and depress the nozzle. Give it a little poke. So sometimes, remember, there can't be 14. Izzy, you're counting, Izzy. So push the little plug out of the methylene blue, and then we're going to create some contaminated water here with an organic substance. So just put a couple of little drops in there. So about 5 drops or so, and then give it a stir. So give that a stir. So you would not drink this water. So this is our now contaminated source. So this is Dan. Dan, are you going to do some jokes at the end? Ella, I'll stick in some jokes. I'll stick in some jokes now if you want. Ella, Ella, quick joke for you. I ate a clock yesterday. It was really time-consuming. Get it? I ate a clock yesterday. It was really time-consuming. Okay, I'll throw some more in. Cool. Right, so now what we're going to do is we're going to test our filter with our organic substance, organic poison, okay? And so what you want to do is draw up into your syringe your polluted water with the organic substance, and then fill up the top of the pipette like so. Okay, so fill up the top of the pipette like that. And what's actually going to happen now, of course, is our contaminated water with our methylene blue in it is now filtering through the sponge at the top, and then through the activated carbon. So through the activated carbon. I know your pots might say charcoal, and it might just say carbon, but this is activated charcoal, or activated carbon. And I'll explain what that is in a second. And then it's going to go down here and then hopefully into our vial. And you should see this is one of the best mechanisms of removing this type of pollution in water. Okay, is methylene blue or toxic or non-toxic? Mindy, it's not a particularly toxic substance, but like all chemicals, of course, you treat it as if it were, but it's not particularly toxic. And it's often used in waters because it's very visible. So they can use it to see, for example, if there's a pipe broken in the road somewhere where there might be a leak. So they put the methylene blue into the water, or any other fluid for that matter, and see where the leak might be appearing. Kate asked, I put in more than 5 drops. Is that okay? Yes, Kate, that's perfectly fine. A little squirt is fine. So just approximation of 5 drops is perfectly fine. What is the most toxic type of water? Tanya, that's an interesting question. The most toxic substance that we know of in terms of the periodic table here, of course, is this one here. Polonium. Polonium is the most toxic of all of the elements, and in fact, you might have heard horribly that a couple of people that were poisoned recently by spies, they were given polonium, and once you've got that, that's it. It's really, really unpleasant. So if you've got polonium in your tea, it's tea time, it's dinner time, it's ZZ time. Don't drink the water. Do not drink that water. Okay, right, if we look, I can see now that most of my liquid has filtered through, look, into my little vial here. And can you see, look, how wonderfully clear compared to the original colour, how wonderful that is. Okay, so here, look, the activated carbon has worked remarkably well on this organic substance, on this organic material. Okay. Has that worked for everybody? Has that worked? Have you seen that? I will explain the science just now. Is that okay? How's everybody doing? It's all gone very silent. Yes, it worked. Awesome, fantastic. Of course, this is MEL Science. Of course it's going to work. Mine hasn't come through yet. Kate, it will definitely come through. Just give it a little bit of time and you'll be fine. So what I'm going to do, if you don't mind, I'll just explain a little bit more of the science. So back in the 18th century, this really incredibly quirky scientist called Henry Cavendish, he was absolutely loopy, and he's massive. He's an incredibly eccentric individual, very wealthy. It needs time. Knows this us. Just okay, sure, Jake. Not a problem, Jake. Everybody, if you're just watching this, perfectly fine, because you can watch it and do it tomorrow. So Henry Cavendish, do look him up, but I'll just tell you one little story about him. He's very wealthy, very, very wealthy. So he had this huge house, but he didn't like talking to people. He really hated talking to people. And his house had loads of servants in it. And so he built in his house a separate staircase at the back of the house where his bedroom was, so that he didn't have to see anybody in his house. So he would use his private staircase to avoid seeing anybody. And on one occasion, a maid was coming down the staircase after cleaning the room, and he went, ah! and shot off. So really interesting character. Anyway, he was the first person to work out that water is composed of hydrogen and oxygen. Okay. This individual, very, very famous antisocial. No, just completely eccentric, completely eccentric, and is of course antisocial. But Endra asked, can you tell if it is plonem? Can you tell if it is plonem? I don't know what plonem is. Plonem. I don't know, it might be a spelling name, or I don't know what plonem is. Maybe this is a different word. Do we ask the question again? I'll come back to it as soon as I can see it. So this individual here is called Avogadro. Lorenzo Romano Amedeo Carlo Avogadro. What a name, eh? On a night out. Tongue twister made from Adam, indeed. But he worked out that although water is made of H and O, oxygen, which is what Cavendish did, it's Avogadro, very famous, of course, for its Avogadro constant. You can look at that on your time. That worked out that it's H2O, so 2 atoms of hydrogen and 1 of oxygen. Okay, I'll come on to the atoms and ions in a second. But I wanted to show you the activated charcoal. So activated charcoal is just like charcoal, but what they do is they take the charcoal and they put it into a massive bin with no oxygen. How did he know? So Ella, I believe he wanted to write polonium. Oh, hang on. Tongue twister name. Yeah, I have to ask the polonium question again. I'm sorry, I didn't see the first bit of it. Is water made from matter? Tanya, is water made from matter? Water is made from hydrogen, so natural hydrogen that occurs. Obviously, it's an element hydrogen and the element oxygen. So you've got two atoms of hydrogen and one atom of oxygen. How did he know? Jake, you need to go and look into lots of... He came up with the idea that you could have diatomic molecules where nobody else thought that was possible. And as soon as he came up with that solved a lot of problems in terms of their observations of chemistry and matter. It has worked now. It's very clear. My audio's dog has given activated charcoal when he ate charcoal. Yes, because the activated charcoal, what they do is they take the charcoal, so just a lump of coal, or a lump of charcoal, and they put it into a bin, and they raise the temperature very, very high, 600, 900 degrees C, without any oxygen present, usually with an argon and nitrogen in it, and they cook it there for ages, and then they drop the temperature, they take it back out, and then they crush it up again, and they put it back into the bin, and they raise the temperature back up to about 600, 700 degrees, with now a bit of oxygen and steam. And that causes a massive fracturing of the carbon, and it creates a massive surface area. So actually our filter here is actually holding onto the molecules of methylene blue, like this, look. It's called adsorption. So what's actually happening? It's working, yay! Is it going to make noise? Yeah, it's amazing. I encourage everybody to look at the science of Cavendish and Avogadro and how chemistry was evolving at those times. Absolutely incredible scientists with massive visions of the world. And that's how it's water. That's worked really well for an organic substance. And you can see from my picture what's actually happening. That little blob in the middle is like a little bit of activated carbon, and the molecules of methylene blue are sticking over the surface of it. So they're just sticking to it. That's called adsorption, not absorption. So when you get a sponge and squeeze up some water, the water goes into the sponge. The chemicals here don't go into the carbon, they just stick on the surface of the carbon. Massive visions and massive names. Indeed, Pranjal, indeed, massive visions and massive names. Yeah. Got a massive name, what shall I do today? I'll do a massive vision thing, you know. Why is water called water? That's an interesting name. It's... a derivation of a very ancient Old Norse word, then from a Germanic word, Wasser, Water, Vita. And if you look up online, you'll actually see how the word has changed over time. Cool. Can I drink the filtered water? Rosalia, as this is a chemistry experiment, you don't put anything in your mouth or don't drink anything, but actually the process here that we just demonstrated is exactly how part of the filtering process works in when they're filtering water and stuff like that. And I'm going to come to this substance in a second, but I just wanted to show you, let's go back a second to the carbon. Okay, right, let's crack on. What I'd like to do now, if you don't mind, can we do the resin one, and then I'll come back to a bit of the science and explain some of the science. Is that okay? Is everybody okay? Everybody okay? It's all gone very quiet, all gone very quiet. Yes. Cool. Nice one. Excellent. Right. So now what we're going to do, so that was a very simple one. Now we're going to do a bit more complicated experiment, filtering mechanism here, before we actually make the bang in the chemistry. So this is the ion exchange resin. Now a lot of you guys and girls probably have houses where there's an ion exchange resin machine in the house, and what this shows you is how that actually works. Okay, and I'll explain the science behind that. So if you just take out your pot, put that to one side, okay, so put that to one side, and then put your methylene blue to one side as well, and your syringe, put that to one side. And now for this one here, okay, we need the following equipment. So you need your 3 other vials. So if you get your 3 other, where is that container gone? Dan, you've lost a container, man. Aha. So not this one, so not the little pot, so not the little pot with the screw top here, the long screw top, not that one. We need that for the bang. What you need is the 3 tiny little medical vials. So if you put those 3 little medical vials into your spongy support, like so. Now the chemicals we need for this one, obviously the most important one is the resin. So that's what we're going to examine. So we're going to explore the resin. So this is another type of filtering mechanism, and I will explain, of course, the science behind that too. You need, again, your little stick. Take a different stick this time. You need another pipette with the top cut off it, so another pipette with the top cut off it. So for this one, we also need a little bit of water. So if you've got some water here, as I have, you also need the copper sulfate. So here is the copper sulfate. So this is the light blue liquid, so not the deep blue liquid, the light blue liquid. Now in this one, what we've got is a inorganic pollutant, a metal. So in the other one, methylene blue is an organic, and I'm going to talk about the polarities, negative and positive. Remember in the beginning, I said that water has a negative and a positive side. So all substances can either be negative or positive, or a bit of negative and positive, and sometimes substances have no charge. So methylene blue actually has no overall charge to the outside of the molecule, whereas this one does. So we're using contaminated, we're going to create copper as the pollutant in this one. Okay, cool. Right, and the last chemical, of course, we need for this one is the ammonium carbonate. So this is the ammonium carbonate. So you need this last little one here, ammonium carbonate. Okay, and before you said that water was blue, but when I searched up the definition of water, it said it was colourless. Why? It's a very interesting statement, actually, Tanny. If you go into online and just say the true colour of water, if you just type into Google or wherever the true colour of water, you'll see that it's blue. But to all intents and purposes, in small volumes, it's effectively a colourless, tasteless liquid at room temperature and pressure. But its true colour is actually blue. Okay, right, so first of all, let's make up our ion exchange resin filter. So if you get your ion exchange resin top off, and then first things first, we need to put a little plug into our pipette. So we need two of these, got one on the top and one on the bottom like the last one. So we're getting a little ion exchange resin filter here. So pop that into there like that. And then as like the last time, just work that into the end of the pipette. So just give it a little tap. You don't need to compress it too much, so just poke it all the way down to the bottom. Now next, you'll see that you can put the top of this into the top of the container containing the resin. So if you just get a nice load of it like that, and you find these little tiny balls, little tiny plastic balls, so just poke them in like that and give it a little tap, 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 and you'll see that they fall nicely down to the end. So then do that again until we've got it up to the 3 mil mark again. So tap, 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 tap. And do have a look in your hands and your fingers. Pull out some of the little beads like that. I'm going to just do that for you now. And I'll just put a couple on the... So if you take out a couple, and using your magnifier, remember the magnifier kit in your general kit. If you get the general kit, the little magnifier like that, put that on your camera, you can actually have a look at that, and you'll see that this resin is loads of little tiny plastic balls, little colourless, little tiny transparent yellow balls, okay? So back to our filter again. I'm just going to top up my filter a little tiny bit more and put a few more of those little tiny resin balls into the top of my filter, okay? And then just give that a little tap down to lock in all of those little balls. Okay. Right, then put your resin, your little tiny sponge bit filter into the top and give that a little squeeze. And I've got a little bit of an excess actually, so I'm going to just tip some of mine out. Just tip some of those out. So I've got a few too many in there. And then put that little tiny filter in there like so. Doesn't make any difference if it's stuck out a little bit. Look, you can see mine stuck out a little bit. So it just compacts our resin into the pipette tube like so. Okay. Everybody okay with that? So then just stick that into there for the moment and put the lid back onto your resin tube. Right, if you then now take another cup, so take out one little cup like so. Now we're going to create our polluted water again, and of course this time we're going to use copper sulfate. So again, if you put into the cup about just half fill it full of cold water, okay, and then identify your copper sulfate. I seem to have misplaced my copper sulfate. No, I haven't. Here it is. And you get a spoon. So what we want with this one is one big spoon of the copper sulfate in the water. Okay, so one big spoon of the copper sulfate into the water. Right, of course, don't forget that you might need to give your little tiny paperclip a wipe. If you're wondering if I'm okay, I will be during the whole life. If you're wondering if I'm okay. Ella, I do, of course. I hope you're all okay, Ella. And it's all making sense, this, anyway. So poke your little... plug into the copper sulfate, and then you want one big scoop of the copper sulfate, okay, into your water. So one big scoop, and that should turn it a nice kind of aqua blue colour. Okay, right. So once you've got that, give that a little stir around to mix up the copper sulfate in that water. So that's what you should have, a nice sort of coloury blue solution. Now, using your other syringe, you then going to draw up 4 millimetres. So 4 millimetres. Look at your syringe. It says 4 to 5 millimetres. So pull up the 4 millimetres or millilitres or centimetres cubed. What inspired you to teach science, Tanny? I grew up in a family full of scientists, and I absolutely love science. I love the natural worlds. That's why I did geology and geochemistry at university, actually, because I love the way in which all of chemistry and physics and biology all work together to make the Earth and everything around us. So I love every aspect of science. And I think for me, geology is one that unified everything. So I didn't have become a pure specialist or a pure chemist or a pure biologist. It's the science that sucks everything up, and you have to understand everything to understand the world around us. Okay, thanks for the question. Thank you. Okay, so if you draw up 4 mils, okay, and put 4 mils in the first one. So just put 4 mils in the first one, okay, like that. So put 4 mils in the first one. And then next, you're going to put, now it doesn't look very dark. It doesn't look very dark this way, so don't panic about that. Don't panic. Don't put excess amount of copper sulfate in, because there is plenty of copper ions in that water. I'm going to come on to ions and atoms in a minute. There are plenty of copper ions because we're going to use another chemical to expose those copper ions, okay? Now the next thing is you put 6 mils, so draw up your full syringe, which is a 5 mil syringe, remember? So drop 5 mils first and put that into the top of your filter like so. So drop 5, and you're going to pull up another one as well, okay? Because of course some of the liquid obviously gets trapped around and soaked into the filter. So fill that up again once it's gone down. So be careful; it won't hold the full 5, so you might have to do a couple of little squirts, like that. And then one last mil of liquid. You want 6 mils in total. So 6 mils in total. Hopefully everybody's okay with that one. So I'm just going to wait for that to drain through a little tiny bit. So this is of course our ion exchange filter. So we've got one to compare. And don't worry, we're going to make it much more brilliant for you in a second. Why is water wet? That is a lovely, lovely, lovely question. I really love that. That's one, Tanya. Why is water wet? If I can just wait for that just for a second, because I want to come on to ions, the negative and the positive sort of side of things, okay, and why things feel wet and why they don't, because that's all about ions and how ions interact with everything. Geography joke, what rocks are never underwater? Dry Nice one, Joe. I've got a couple more jokes yet. Just do this one and I'll crack a few more jokes. Right, so we've got that one. The next thing we need to do, of course, is we're going to add a chemical to both of these kind of solutions here. So once that's drained through, can you see the heights are the same height, more or less? So once you've drained through, can you just remove your filter and put it into the third little vesicle, so little vial. So take your filter and put it into the third vial, okay? Can you just repeat what we should have in the vials, please? Toby, of course I can, yeah. So this one here, the first vial, should just have copper sulfate, dilute copper sulfate solution. So that should be there. This solution here should just have the filtrate, i.e. this substance that's gone through the ion resin, okay, the ion exchange resin. So key words there, ion exchange resin. And in the third one, there should be nothing just yet, okay? Because what we're going to do now is we're going to use some ammonium carbonate. So if you can get the ammonium carbonate, if I just turn that the right way, everybody wants, that's the next one. So this is, we've got 5 drops. So 5 drops of this, 5 drops, okay, into the first one, 5 drops into the second one, and then fill that one with the remainder of the solution in the ammonium carbonate, okay? So fill that one with the ammonium carbonate. So 5 drops in here, 5 drops in here, and fill that one. I'll do that again. Of the ammonium carbonate, you put 5 drops in the first one, 5 drops in the second one, and fill it. What's your favourite chemical substance? Tanny, my favourite chemical substance is in fact water. It's the most amazing chemical in the universe, without any doubt at all. And why? Without water, nothing works. Your whole body depends on water. Everything on the planet depends on water. And Tani, here's a question for you, Tani, and a question for all the audience, of course. Water is one of the few substances that actually becomes less dense when it freezes. It becomes less dense when it becomes a solid. How curious is that? Now that has an incredibly important impact on life on the planet. Just think, why is it very important for ice to become less dense when it becomes a solid for life on the planet? It does, and it does. Water molecules expand, the little bonds, and I'll come back onto that. Okay, so back to the chemistry, guys, just and girls, for a couple of seconds. So 5 drops in 1, so 1, 2, 3, 4, 5. And can you see now it's gone wonderfully dark, and give that a little stir. Can you see how nice and beautifully blue and dark that has become? And then 5 drops into the filtered one, so 1, 2, 3, 4, 5. And look at that, capable not to stir it with the contaminated end of your stick. Okay, you can see that there's absolutely no copper ions in that. And actually, look, if you fill then the last one with the ammonium carbonate, so fill the last one with the ammonium carbonate. Whoops, my little filter's come a little unstuck there, so I'm just going to pop that down again. So fill that full ammonium carbonate, and you should see beautifully, can you see, look, as the ammonium carbonate is trickling through our resin, look, you get this little blue line creeping down like a little silent wave down into the resin column. And then look at the bottom, look at the colour. Look at the colour at the bottom of our third tube. Now I will bring that up to show you, because I've got a sneaky question for you, sneaky question. Seas would freeze. Not quite, Yuzi. I love that suggestion, that question, that answer. That's a lovely, good suggestion, but not quite right. What would the Earth look like with that water? It would look like Mars. We've just landed on Mars, and you can see what Mars is like. Barren, dry. What would the... Tani, it's fine. This is what the live webinars are for asking those questions, which is great. Okay, cool. If I just bring that up to you to show you, you can see here, look, this one's really blue because that was heavily contaminated, so that's lots of copper in that. And actually what the ammonium carbonate was doing, is what's called a qualitative test. So the ammonium actually ions react with the copper to go, oh my gosh, and they form an ammonium copper compound, which is very blue. And that gives you a real clear sense that there are copper ions in the water, pollutant. But can you see in our filtered one, there is no blue at all. So our resin filtered out all of the copper ions from the solution. And then look here, interestingly, when we put the whole of the ammonium carbonate down through the resin column here, look, the water was partially blue, a little bit blue. I don't know if you can see that. Can you see it's a little bit blue? Now that is interesting. That's an interesting property here about ammonium carbonate and our resin. Okay, and our resin. I'll just put that there for a side. Okay, cool. Is everybody okay for the moment? Everybody okay for the moment? What is the most popular method for cleaning our water in the UK? Jay, in water in the UK uses massive rock filters, then it uses carbon filters, then it uses chemical filters, chemical treatment, resin filters, right? And then it's chemically treated to purify it and kill any bacteria and stuff like that, so with chlorine and things of that nature. Okay, endo. Cool. Right, can I just quickly share a slideshow? Can I just ask, because we're covering a lot of science here and a lot of chemistry. A lot of science and a lot of chemistry. Is everybody okay if I just spend a couple of seconds explaining some of the critical science here, if that's okay with everybody? Yeah, okay, cool, brilliant. Okay, you've heard me mention atoms and ions a lot, okay, does it have? Yes, it does, Scott. In some cases they do treat the water with UV. Well done, Scott, yeah, they do, but not all the time. Yep, Julie, cool. What's deadlier, arsenic or impure water? Arsenic on its own is it's a nasty toxin, very, very nasty toxin. And I can tell you a little story about arsenopyrite shortly. But impure water depends what the impurity is. Because some impurities, for example, salt isn't toxic, so you can actually drink salty water, that won't kill you. If you drink lots of salty water, it will. Okay, cool. Right, if I could just go back to atoms and ions. So you've heard me saying we have to drop off early in Florida, but we are really appreciate your enthusiasm. Brian, it's not a problem. There's a recorded lessons, but you're going to miss the bang. You're going to miss the bang, the last experiment at the end. But please, please, please do watch the webinar when you record. Anyway, have a lovely day, and I shall hopefully see you next week. Cool. Goodbye. Mind-blowing questions. What is your favourite? Mind-blowing questions. What? I don't believe in the Big Bang. I'm a bunch of scientists that don't believe in the Big Bang. A load of people believe in the Big Bang. I don't believe in the Big Bang. I'm very happy for there to have been we don't have to have a beginning, and we don't have to have an end. It's an evolving flux, so I'm not happy with that. So here's a point of contention already. But if you ask any scientist that believe in the Big Bang what becomes before the Big Bang, their conversation becomes a bit... And then what's space expanding into? Then the conversation, I don't know. I don't like don't know answers, so yeah. Anyway, cool. Right, I talked about atoms and ions. So if you get... gold, so for example, if you get a molecule or a handful of gold, there's no charge on the outside. The atoms themselves, atoms of gold, have no charge. So it's a bit like when you have a magnet, if you have a north and a south pole, they stick together. So if north and pole stick together, if you have a north pole and a north pole, they repel, okay? So in a very similar way, if there's no charge, nothing's going to happen. So the atom won't do anything, won't respond. But if one ion has a missing electron, it's very positive, it has an extra electron, it becomes negative. Okay, so atoms that have missing or additional electrons are ions. Okay, so some substances are ionic, and some substances are covalent, and some substances have no charge on the outside. Okay, so if we look at, for example, sodium, when it reacts with chlorine, up here, look, okay, to form sodium chloride, which is salt, the salt you put in food, sodium chloride, the sodium ion gives its electrons, so it becomes positive ion, and the chlorine takes the electron and it becomes negative, it becomes a negative ion, so positive and negative ions. Is that okay? Also, okay. Is everybody okay with that? So everybody's okay with the fact you can have positive sides to an atom and negative sides to an atom. Okay, so negative and positive, yeah? So if we look again, you've all seen salt, I know you've all dissolved salt in water. So I'll just get to this, look. I'll come back to the polar things. So when you dissolve salt in water, look, what happens is the sodium ion is positive, but water, it's a beautiful, wonderful, universal solvent, this incredible chemical. So water itself has a negative side and a positive side. So when you pour a little salt into a little glass, okay, the sodium goes, oh my gosh! And the negative side of the water molecule, the oxygen, rips the sodium out of the salt, and then the positive side of the water molecule, the hydrogen, rips the chlorine out, because the chlorine's negative and the hydrogen's positive. Rip! And that's why it dissolves, that's why substances dissolve, because there's polarity. The salt is a polar substance, and the water is a polar substance, so they're very happy. Yes, it is. Chlorine is lovely, I love that idea. It's an electron thief, it plucks out those, so it makes polar. Now, when things are not polar, you can't have a polar substance dissolve in a polar substance. So non-polar solvent will not dissolve salt, which is a polar substance, okay? And that's what all of these, of the resin is about. The resin itself is taking very happily a polar substance. But if you put, as in the case here, look, if you put, look, for example, the ammonium carbonate, it's partly polar and partly not polar, and so some of it will be taken out, but not all of it, because the resin itself only works on polar substances. So here, you actually have to use the carbon filter. I'll just bring that back. You'd actually have to use the carbon filter to pull that material out, okay, the methylene blue, or the ammonium carbonate. So you need to, when you're treating impurities in water, you need, lots of different types of filters. I think maybe see in the conversation there, Jake, one of our students, our regular students, was absolutely amazing, and he says, how is water treated in the UK? Well, they have to put it through a whole load of different filters. So some pull out the polar substances, some pull out the non-polar substances, and then some basically just pull out all the big material anyway that doesn't dissolve in the water anyway. Okay. Why do our fingers crinkle in the swimming pool or in water generally? Tanny, going off topic a little bit, Tanny, but the reason that your fingers go crinkly in the water when you have a bath or you put your hands into water for a long period of time is that the surface layer of your skin, absorbs water. It becomes more hydrated. Okay, so the water gets in there, goes, yippee! And as a consequence of that, it expands. It becomes expansive. So in order to create the bigger surface area, to accommodate the bigger surface area, the skin itself becomes undulating, so it increases its surface area. So water is expanding because it's absorbed a little bit of water and it has to become crinkly. That's why when you stand outside the bath in front of the dry and warm your hands again, the water evaporates and your hands go back to or the skin go back to the same level again. Cool, I hope that expands. So to explain how the resin works, before we get on to the bang, and I promise we're going to do a bang. Okay, explain how the resin works. Those little plastic beads, they're made of that chemical here. It's a very complicated polymer, but you don't need to know about their chemistry particularly. But on the outside of the polymer, the little sodium ions, and that when they go into water and other ions come along like copper or magnesium or calcium, they go, oh, I lose one of my sodium ions, lose that sodium ion, but replace that with those other ones. They're more exciting. So the resin itself becomes a kind of selective thief. It pulls out the charged ions from the water. So that's how the resin works. It pulls out the charged ions. And so you've also, has anybody boiled a kettle and seen fur, the sort of white crystal fur inside the kettle? Anybody? Yes, of course. Lovely, 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 yeah. So those are all fantastic, guys. Thank you, Laura, and thanks, Scott and Ella. Those are things, those are impurities in the water, and that's what the ion exchange resin would do. It would pull out the magnesium and the calcium and stuff like that that are actually the impurities around the furry bit in your kettle, okay? Yes, and especially is it in Cambridge. It's quite soft water there, hard water. And so hard water's got lots of dissolved stuff in it. It's much better for you than soft water, which has hardly got anything in it, okay, just H2O. Right. Let's get on with experiment number 3. Why do most swimming pools have to have chlorine? At Tanny, they put chlorine in swimming pools simply to kill microbes. So the chlorine ions effectively interfere with the protein coat of bacteria and viruses and stuff like that, and they basically cut little holes in it and it kills the bacteria in advance. So that's why they put chlorine, or in some cases they put ozone that does a similar thing in swimming pools. Right, let's get on to experiment number 3. This is bang. So this is the bang one, okay? So I've just swatched cameras again. So this is what we're going to do now, oxyhydrogen. Now coming back to Cavendish, Cavendish was the first person to create this experiment, so you're actually going to create or recreate one of the most important experiments in chemistry, the discovery of the components of water. So let's get all this set up. So move that aside. Okay, this is where you need your boiling water, guys and girls. So you need your boiling water here. So put that to one side. We need our beaker, it's a big beaker. I'll just get this one tidied up, put our ammonium carbonate away. So for this one, we need the sodium carbonate. Wherever my sodium carbonate has gone. Everybody okay? Okay. So we need our battery pack, we need our 4 cells. Okay, so don't forget these are individual cells, they will make up a battery. I'm going to move that out of the way. So we need our sodium carbonate. So that's the first chemical we need. So sodium carbonate, I'll just bring that up and show you. So sodium carbonate, like that. We also need our calcium hydroxide. So a little bit of calcium hydroxide. Okay, move that one to one side, it's just fallen over. We also need our lead. So this is our little lead. So this is the bang bit. So we need our lead. We also need access to some matches. You will need your scissors, access to your scissors. I'll just move that one back into view. So this is the one we're doing now. You also need little tiny black rings that come in your pack. So if you just get a little black ring into your pack, so just take that out. And I'll show you what to do with that. So pop that out like that. Okay. We need our little holder, so a little holder for one of these containers. We also need the little tiny, now this is a sturdy polycarbonate pot, so we need that little tiny sturdy polycarbonate pot. We also need, of course, our leads, our little crock clip leads. So if you just pull those out and just straighten them up a little bit, so pull those out and straighten them up a little bit. They might sort of curl back in a little bit, but just give them a little sort of straighten. Okay. We also need our little tiny one-hole bung, so one-hole bung here. And now this time, we also need Is everybody okay? It's quite busy, this one. It's quite busy, this one. We need the last of your pipettes, the cup pipettes. Now, don't forget, with the other pipettes, you can repeat the experiments, but you also need to just wash them out with warm water. Is perfectly fine, warm soapy water. You also need the pipette that hasn't been cut, so the whole one, okay? So the pipette that hasn't been cut. And you need the filters, so little filter papers, so we need one of those. And we also need the candle. So we'll do the first little things first, is put the candle in the one-hole bung. So put the candle, look, into the one-hole bung and use that as a little mounting. And a little joke, just as an aside, very, very quickly. A little joke as an aside. What is this? What is that? What is that? Wax, not quite. What are those? A candle? How many? How many? 4? No, that's a 4 candle. Classic joke, give me an old joke. That's a 4 candle. Those are 4 candles. Yes, I shall do it. 4 candles, get it? Nice, classic joke, couldn't resist the temptation with your kit. Anyway, we're only going to be using 1 candle today. Oh, and just before we crack on with this bang, I know we're running a little bit longer than the hour, but we'll be done soon, but this bang is wonderful. If you would like, hello Ronnie, indeed. If you would like to receive a little personalised note from me for attending this pure water thing, please just follow the link in the chat in the web link and just fill in the details there, and I will send you a little personalised thing to say, hey, thanks very much for attending this particular pure water webinar, and see the little things that you've learned along the way. Okay, so back to the preparation. Okay, so back to the preparation. A little bit of a mess there with my resin flying about all over the place. Okay, so I think we've got everything more or less ready for this one. So don't forget you've got your matches or your lighter. So if you could also now put your battery together. So remember, and it's really important that you make sure the batteries are nice and fresh, okay? So here, if you put the springy end, don't forget, is the negative end. So that's the flat end of the cell. And then put another one, I'm dropping them everywhere. And then another one there, and then another one there. Okay, cool. So that's set up our little battery pack. Make sure that with your little teeth, your little crocodile clip teeth, that the red ones, okay, that the teeth connects to the metal on the thing. So you can see here on the lead, look, there's some plastic covering, some insulation covering. Make sure that you connect up the red to the metal. And then similarly, the black to the black bit of metal at the end of the lead. So make sure it doesn't go onto the insulated terminal. Okay, cool. Right, then, can I also point out, look, if you look at your end of your little tiny electrode here, if you look at the electrode, can everybody see there's a little tiny short piece of metal that's coming out of the electrode, and then the one at the end here. So the short one here is black. So the black one gets connected to that side, and the red one gets connected to that side in time. Okay, so I'll click around. The other one is the white in the set. If you've got a white one, the white one will be the equivalent of what's the other colour you've got? You've got white and black. Yeah, the white one's equivalent to the red. Yeah, that's exactly right, Ella. Thank you. And yeah, the white one will be equivalent to the red. So here, you put the black one or the white, red one. The black one here, and the red one on the end of the long one. So we'll just move that to one side. Okay, next thing's next. We take our pipette. So if you take your pipette, look, and see this little nosy bit here. See where it starts where it says 0.5. If you get your scissors, I'll just put that into view. Get your scissors and cut at the 0.5. So just cut the end off your pipette like that. All right. So cut the end off your pipette like so. Okay with that one? Right. So next, now we've got to start the chemistry going. We've got to start this chemical reaction because it takes a couple of minutes to get the chemical reaction going. Okay, what you then need to do is take the lid off the calcium hydroxide. So give it a little tap. Take the lid off the calcium hydroxide. So the calcium hydroxide, guys and girls. So calcium hydroxide, just take the lid off that one. But don't throw the lid away because we need that back in a second. Then put your little tiny pot controller, if you like, the pot lead. So screw that right down onto the pot like that. So pop that like that. Okay, so pop that into there like that. Now we need to take the sodium carbonate. So you take the sodium carbonate. Now we might need to depress the little sort of safety plug in that one. So just take that lead off there, that lid off, hopefully. Mine takes a little bit of screwing to get this one off. There we go. Now I need to depress the little lead on this one. And go. Cool. So again, just put the little bit of, depress the little tiny security plug in the top of that one down there, so do that. Okay. Now you're going to put the whole of this bottle into the whole of the bottle, look, into the calcium hydroxide. So the whole of that bottle, okay? So squirt the whole of that in there like that. So whole of that there like that. And then put your lid back on firmly. So put your lid back on firmly. So screw that all the way down tight. Make sure it's nice and tight. Okay? And give that a really good shake. So give that a really good shake. Now I'm going to come back to shaking that because you also now need to put the hot water into your container here. Okay? So what we're going to do, we're actually creating an alkali in this reaction here. We're actually creating sodium hydroxide, which is the substance we want, and we're going to have to filter that because it's quite cloudy, as you can probably see. Okay? Does it have to be hot? Ella, the hot water needs to be as hot as it can get. So if you can get some boiling water, of course, be very careful with boiling water. But if it can be really, really, really hot, the hotter it gets, the better it is. Okay? So give that a really good shake. Now, because it's going to be hot, we need to stick on our little thermal. You're very welcome, Ella. It's a pleasure. So stick on your little thermal thermochromic sticker just to show you that it's hot. This liquid's hot. So pop that onto there like so. Not very straight, Dan, not very straight at all, but at least it'll work. So you can see here there's nothing there. There's no yellow marks in the middle, so it means it's quite cool. And we'll come back to this one, give a good little shake for about a minute here, look. So shake, 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 shake that, shake, 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 shake. And whilst that's shaking, I'll just explain a bit more of the science that's going on here. So remember before, I said it's a qualitative test. You've got these different metal ions. So each different metal, if you add substances to it, like ammonium compounds, for example, they give different colours. That's how you detect what kind of contaminant might be in a sample or what kind of metal might be present in a sample, okay? And I'll come back to little fake news at the end, okay? Are we putting acid on the batteries? No, 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 don't put any acid on the batteries, Ender. No, not just yet. Right, let me get back to this so I can just show you what to do. Right, so we're going to shake that for about a minute. Okay, so about a minute, good lots of shaking. Now put the hot water, so half fill your plastic container. So half fill your plastic container with water. So about half fill like that. So I've got really hot water like that. And then suspend the whole of this apparatus in the hot water. So suspend the whole of the apparatus like that in the container. Okay, so that's what that should look. I'll just bring that up to show everybody. So suspend the whole of the container into the hot water. Is that okay? So I'm just going to pour a little bit of that out actually. Okay, and we're going to leave that cooking for, and hopefully here, you can see on the side that my little tiny thermochromic film, look, has told me it's nice and hot in there, okay? Now we're going to wait a little bit for that to sort of cool down for a second. So while we're doing that, we need to set up the filter, okay? Is that the experiment? Oh, no, 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 no. What we're doing is we're creating the experiment here to make the bang. So what we need, effectively, what we're trying to do here is create we're going to react sodium hydroxide, okay? We're going to react sodium hydroxide, to create sodium hydroxide rather, and then we're going to electrolyze that, and when we electrolyze sodium hydroxide, it'll create oxygen and hydrogen gas, so we're going to create oxygen and hydrogen, which is called oxyhydrogen, and then we're going to pass that gas mixture over a flame, or by a flame, and it should, hopefully, and as I said before, nerves of steel, bang! It should go bang, I hope, when oxygen, the bonds of oxygen O2 and the bonds of H2 break and then form H2O, we should have a very exciting, so I did say to you, have nerves of steel, okay? So hopefully that's worked okay for you guys. So just leave that for about another couple of seconds. Just a couple of seconds. Right, so now what we need to do is create the filter funnel, okay? Boom! So I know this is sort of taking slightly longer than the normal sort of MEL sort of science things. Is everybody okay? Is everybody okay so far? Nobody. You've all run off. Yep. Scott, lovely. Okay, cool. Ooh, excellent. I'm just going to put a little bit of that out. Well, yeah. Fantastic. Cool. Thanks, Toby. Thanks, Tim. Thanks, Ella. Right, so let's just have a little look at that. That has definitely reacted really wonderfully well. I'll just stick that in there for a minute or two. Right, so where have I put my filter funnel, Dan? Okay, so filter funnel. So we get our filter funnel out. Arthur, how did the warning test sticker change? This is what's called a thermochromic film, a sort of thermochromic film, Julie. And what happens is that when something's heated, it changes its molecular structure, and that molecular structure changes the way that light interacts with it. Okay, and as it cools, that structure changes. The molecules vibrate back into its original structure, and that again changes how light interacts with it. Hurry up, Dan! I've got cake waiting for you. Cake! Where's the cake, Jake? Right, quickly then. The bang's coming. Literally, we're seconds away from the bang. So if you get your filter funnel like this, so take your filter paper out like that and stick the filter in like that. So put that into the filter funnel. You then stick, so what we're trying to get here is the sodium hydroxide, and if we take this now out, if you take this out, undo the bottle. In fact, just give it a little shake first, just give it a little tiny shake, and undo the top carefully, and then pop that into the, there we go, and filter that liquid out. So the liquid's coming out here is sodium hydroxide, and that's what we're going to electrolyze, okay? That's the liquid we're going to electrolyze. While it's doing that, chuck this water out. So chuck this water out, because we're going to use this to support the electrode, okay? I'm just going to give that a little wipe. You don't have to give it a little wipe, but I'm just going to give mine a little wipe. Just a little dry that off. Okay. So hopefully yours is filtering. Hopefully everybody else is filtering successfully. So you can see that there's residual white gunk in there, and actually that white gunk is basically chalk. It's calcium carbonate that's formed in this reaction. So just give that a couple more seconds to filter out. So we've got a little bit of a filtrate there. Right, whilst that's doing its filtering business, okay, we need to set up our electrode. So if you get your little your little rubber bung, so get your little rubber bung, and you're going to loop it. We're going to use this to seal up the end of the pipette. So just loop the whole lot through, look, the end like this of your electrode, and the negative one there, look. And then just pull the black rubber bung, look, along the end. And once you've got it to the end, look, just wriggle it up the base of the electrode, like so. So wriggle it up the base of the electrode to the middle bit there, look. So just get it up to there. So that's what you're creating. And we're going to get a bang in a minute. Tiny, bang in a second, I promise. So here's wriggle that all the way up to the end of the electrode like so. All right. So we're almost done with our filtering. Now what we need to do is remember the pipette that we cut the nose off, If you then insert, look, the electrode into the end of the, and so push that like that. So push it until it's nice and snug, look, and it's the end of the pipette, look, has fit it over the top of the little rubber seal. Okay, poor pipette. Indeed, but it's a very exciting pipette in a minute. Okay, great. So now what you need to do then is pop that into your plastic container, and then, okay, we then need our other pipette. So get our other little pipette, the one that works, okay, the one that works, well, they're all working pipettes really. Okay, and if we put this to one side, so put our filter to one side, you'll now notice that you've got a whole load of sodium hydroxide in here. So we remove that from the base of our conical flask and put it into the and then put that, look, into the pipette like so. So you might have to work a little bit hard to squeeze the last little bits of the sodium hydroxide in there, so put that all into there like so. Okay. Everybody okay with that? You cut its nose off. I did cut its nose off. I just shortened it a little bit. Okay, right. Move everything else out of the way, because we're shortly now going to explore the oxyhydrogen bang. Okay. So we now need to connect up our little electrolytic cell. I'm just going to cut a little bit more off the nose of my pipette, a little bit like that. So now what you need to do is put your plastic, hard plastic pot onto the top of the container like so. I'll just bring that up so everybody can see that setup. If everybody can see that setup, I hope that's okay for everybody. So all I've done, look, is put that hard pot over the top of the electrolytic cell, effectively. And boom time is coming. So then connect up your electricity, so black one on the short electrode like that, and then the red one on the, and then hopefully you should see immediately, can you see immediately there's fizzing? I'll just see if I can bring that up to show you. There looks like fizzing, look, on the electrode there. So that's electricity is passing through that solution, and it's splitting apart water into oxygen and hydrogen. So splitting apart water into oxygen and hydrogen. So that's what you should be getting. Now there's some blue chemical form there because actually the sodium hydroxide is actually reacting on my one with the copper to form copper hydroxide. Now we don't worry about that. But it is creating lots of bubbles of hydrogen and oxygen. So wait for 3 minutes, guys, now. 3 minutes, I'm almost done to boom time. And so we need to light our little candle. So light your candle. So light our candle. Okay. Now I have warned you before, and because we've got matches, we just need to take our gloves off for this one. So before we've got matches, just need to take our gloves off. Now what you're going to do is you're going to see with the matches, if my finger was a match, you're just going to put the pot, the mouth of the pot very quickly, so take it off and put it quickly close to the to the lit candle, and see what happens when we do that. Okay, is everybody ready for a bit of a boom? 5, 4, 3, 2, okay, so cool. So that's electrolyzing wonderfully. Right, ready? 1, 2, 3. So you do it fairly quickly. Woo! Boom! I'm going to repeat that because I've still got plenty of electrolysis going on. I'm going to repeat that, and then I'm going to turn the lights off to do it. How is that? You should hopefully have got a really nice explosion. So do it quickly and take it off and go bang, and you should get a really nice bang. I don't know if anyone's got a bang just yet. Ella, that is so cool. This is absolutely wonderfully cool chemistry. That's what you expect from MEL Chemistry. This is absolutely wonderful front-end stuff, okay? So I've still got quite a lot of electrolysis going on. I've got a lot of gas going on. So I'm going to wait about a minute or two for my gas to accumulate in a pot again. Okay. And then what I might do is just end the slideshow a little bit with A little bit of fake news for you to read. Because the other name for water, of course, is dihydrogen monoxide. So if you say to somebody, I think I have a little glass of dihydrogen monoxide, they go, what? That sounds really toxic. And actually, that's just a name for water. So you could actually create a bit of fake news with that little link. We didn't get a bang. You didn't get a bang. Wait for three minutes, and you should when you bring the top off and you bring it close to the match. When you bring it must go quickly, so bring it up close to the match really quickly. I'll do it again for you. And I'm going to turn the lights down a little bit. You should get a really nice bang, bang. Okay, I'll just turn the lights down. Hopefully, in fact, what I might do, because it's quite dark in here, if I disappear with the lights, you won't see. Oh, the candle will be there, that's fine. Okay, so I've got my candle, and I'm just going to take this pot off again, look, and show you what should happen, hopefully. Bang! And hopefully that's worked for everybody. Boom! Kaboom! Isn't that amazing? And of course that experiment was conducted by Cavendish in the late or mid to late 18th century. And can you imagine his joy when the first person to see that combination of oxygen and hydrogen and put a spark in it, bang! Now when I'm teaching in school, normally I have a really big balloon of oxygen and hydrogen, and I can tell you it is the most satisfying bang you can practically produce. It is awesome. Anyway, so I hope that's been okay. It is awesome, Ellie. I hope that's been interesting. I hope I've managed to explain things to you. With this bit of kit here, just disconnect the batteries when you're finished. It pushed the flame out. That flame released a lot amount of energy and a huge spark of gas. It did actually push out the flame. So this liquid in here, when the liquid in here, with your gloves on this point, with the liquid in here, throw that lot away, okay, and then just give the electrode a little bit of a rinse. But you've got two electrodes, so you can do it at a separate time, and then that just throw that away. You can or recycle that, okay. But do disconnect the batteries, not to let it keep going. Okay, so pure water, it's important. You've learned how to filter some organic chemicals with the carbon filter, some inorganic chemicals with the ion exchange resin that takes the other ions that you don't want, the poisons and toxins and stuff like that, and just chucks some harmless sodium into the water. And we've also split water apart to produce hydrogen and oxygen, and then recombined it to make it go bang! So, I hope that was okay. Thanks for another awesome lesson, Dan. Thanks for giving up your Saturday evening and classic 2 running joke to Tam, Fran and Nick. And cake, don't forget your cake. We need more pure, we do, Ella, we need more pure water. But now you know how to go do it. So, once again, guys and girls, thank you so much for joining. Thanks for signing up to MEL. I hope to see you next Saturday. You've got Mark on tomorrow, Sparky Mark with some physics stuff. And stay well, stay safe, enjoy the rest of your weekend. Love you lots, and I shall say goodbye.